So I'm going to talk about some of my work in the last year that I did as part of my PhD thesis, which I'm calling Towards 4D Perception with Foundational Priors. So I want to start by showing you this video of a person driving on the streets of Mumbai in India. And specifically, I'm showing you negotiation between lots of vehicles at a speed bump. And once you look at this video carefully, you'll see that there's so much going on. There are different cars that are moving at different paces. There's a truck that suddenly appears in the scene from the right. And then there's motorcyclists, for example, this one that moves faster than everyone else, or the motorcyclist which is occluded and then eventually reappears in front of the ego car. So all of these actors in the world are still able to coordinate their navigation and drive safely. So clearly we humans have a really rich understanding of this dynamic 3D world around us, right? We, for example, know approximately how the world is structured or how different things are moving around us. And we also have the ability to make objects persist over time, even when they might not be observable. So for example, for this motorcyclist that undergoes a near full occlusion and eventually drives right in front of this ego car, we are able to estimate how it must be moving over time while it is not visible. And then we understand that it is eventually going to reappear. And more often than not, we are constantly replaying these kind of events in our mind over and over, and we are reasoning about counterfactuals. So this could be different ways that other objects in the scene could move in the future, or this may be replaying the same events, but while taking different actions. So for example, what if I had driven a little bit more to the left? How the world would look like from here and how the other agents in the scene would react differently. So humans can reason about all these concepts and are therefore able to safely interact with the dynamic 3D environment. And this is sort of the North Star that I'm going to work towards today. So one of the first things we want to ask ourselves is, how do we build this reasoning in our vision algorithms so that they can similarly perceive the 4D world the way we do? And the gold standard, like most other supervised image and video tasks, would be to get access to true 4D data, which means that for any scene, we would want the 3D location of every point in the scene and the calibration of sensors from which this scene was captured. And it's kind of not unreasonable to expect this, as there are these upcoming class of sensors like 4D LiDARs that give you exactly this kind of data. Or you can always go all in and collect scenes yourself by building classical multi-view setups that can post hoc give you the structure of the scene. And then supervision with this 4D data is not all, right? You might want to also bake in priors about how the world unfolds. And this could be maybe by using forward models that represent the physical laws of how this data was generated in the first place. So this could be tools from inverse graphics like differentiable volume rendering, or we might want to simulate the physics of how sensors like RGB cameras or LiDARs operate themselves. But you would agree that this approach does not scale up, right? We have not yet hit the ImageNet moment for 4D datasets. And to put things into perspective, this is how much 2D image and video datasets we have today, one of the largest of them being Lion 5 billion. And in comparison, there's much lesser amount of 3D data, the largest source being the 10 million assets from the Observer's Excel dataset. And there's even lesser number of 4D datasets where you have access to some kind of 3D information of the scene over time, registered into a global coordinate frame. So the kind of success that we have seen for 2D tasks cannot easily be translated to 4D tasks because we are missing the key ingredient, which is lots of data. So what I want to argue today is that instead of relying on gold standard 4D data, we should leverage the internet collection of 2D videos because they serve as a really good proxy for observations of this 4D world. Now, instead of thinking about billions of these videos as raw and unprocessed data, it's useful to realize that all of these priors or all this information has already been distilled into foundation models. And these foundation models have used the video sources to achieve tasks like modeling the generative distribution of real-world scenes by synthesizing videos themselves, or estimating the geometry of a scene, or tracking objects over time, even through complex interactions. So by learning these tasks, foundation models have formed rich internal representations or priors about how our world looks, moves, or is structured, which naturally raises the question, could we repurpose those same priors for understanding the 4D world? So this is the direction I head towards with my thesis, which started in the pre-foundation model era when ultra large-scale training was not a thing. So at the time, I explored how one could learn scalable pre-training tasks like next time step prediction. And for this, I trained lightweight architectures from scratch using 4D data in the form of LiDAR sequences. And then I used this next time step prediction model or a forecasting model for downstream motion planning for autonomous scenes. After this, with the advent of foundation models, I tried applying the data-driven priors from these models zero shot to tasks that were too under-constrained to be solved before. For example, tracking people through occlusions in 3D or reconstructing dynamic scenes from sparse views. And since I talked about most of these approaches in my proposal, in today's defense talk, I will instead focus on how we can go ahead and actually capitalize on the real-world priors learned by foundation models, specifically video generative models in this case, and fine-tune them with minimal amount of data. So to start with, I will first discuss a simpler version of the perception problem, which I'm calling 2.1D layered perception, where we essentially try to estimate the extent of an object during its occlusion. And then I will move on to discussing more recent work on understanding the 3D structure of a scene through the task of novel view synthesis. So let's dive into the first part. Okay, like I said, here we are looking at de-occluding objects. And unlike state-of-the-art segmentation methods like SAM2, which segment only the visible or the modal region of an object, we want to estimate what the extent of this object would be even under partial or full occlusion. So for example, for this laptop on the left, which gets fully occluded in a few frames, we want to predict on the right a plausible amodal mask for all of these frames where it is partially or fully occluded. And then not only this, as our end goal, we want to fill these amodal masks in with what the object's appearance could have been. So I'll start by talking only about segmentation first. So amodal segmentation is not a straightforward task because when an object is occluded, there are multiple explanations for what could be behind the occluder. So for example, a partially visible arm and head here could be belonging to a person that's either sitting or standing. And both of these are consistent explanations. So this ambiguity makes our prediction task inherently a multimodal problem, which means that there isn't a single correct answer, but rather a distribution of plausible shapes and appearances of this object. So there is prior work that handles this multimodality. But most of these models are image-based, which introduces a few limitations. So one of the limitations of image-based models is that they cannot work in heavy occlusion, because you can imagine now you'll get very little visual evidence for the visible parts of the objects. And in cases of complete occlusion, the object is not going to be visible at all. And then across time, these single image methods are inconsistent because they are not using the context from the neighboring frames. So an obvious approach is to formulate amodal segmentation as a generative task and use video models for the same. And in this particular work, we start from a pre-trained stable video diffusion model, which we then fine-tune. It turns out that it is frustratingly straightforward to fine-tune video diffusion models for this task. All you have to do is input the binary modal mask of the object of interest and the pseudo depth of the entire scene, and then fine-tune this model to predict A-modal masks for the object of interest. Now, I know I did not motivate adding depth of the scene as an input, but we'll come back to this in a bit. Now, you'd wonder where we would get the ground truth A-modal mask annotations for this task. Of course, it is hard to find real-world labeled data for this, so we have to turn to synthetic sources like the SailVOS dataset, which is rendered from game engines, and so therefore you have access to precise ground truth A-modal masks. So once you have this data, all it takes is about 20,000 total training samples and just 1 day of fine-tuning on 8 A6000 GPUs. So first, I want to start by showing you some in-distribution results on the validation set of SailVOS. Starting from the sample video from SailVOS, I'm showing you the original RGB image on the top left, and then the visible masks or the modal masks of this person on the top right, the predictions from our model on the bottom left, and then the ground truth A-modal mask. So you'll see that even though in this example, the person is heavily occluded and only their torso is visible, the model has sufficient cues from just viewing the torso that this is in fact a human. And so it knows how to predict 2 legs, and even the orientation of the feet is quite realistic. Similarly, here are some more results and comparisons with baselines. And for this analysis, we'll evaluate the quality of A-modal segmentation using the MIOU, or the mean intersection over union metric, which averages the performance across all frames of a video. So again, for reference, that is the original image. The second column is the input modal mask, A-modal ground truth. And then, as you can see here, our method produces quite realistic masks as compared to the ground truth. It doesn't have to follow exactly the ground truth because there are multiple plausible solutions, but it does fairly well. And we also benchmark an image-based method called PCNet-M, which, because it is a single frame method, it is inconsistent over time. And we also compare to a video baseline, which is regression-based. And so as expected, it kind of regresses to the mean of the entire distribution. And so you see the outputs are quite patchy. Okay, so the most exciting part of this work is that when we test our model trained only on synthetic data, 0 shot on the real world, from on a data set called Tau model, which has real world videos, our model is able to generalize surprisingly well. So to start with, I'm showing you an example from Tau A model, which is a similar case as I showed before for SailVOS, where only the torso of a human is visible. And then I want to point out actually that Tau A model has 8 times as many object categories as SailVOS, which means that even for new object categories, for example, cows in this case, our model is able to predict consistent A-modal masks very well. And this is another example of a new category, a trash bag. It is a static object throughout, but it undergoes much higher degrees of occlusion. And finally, this is another example of a person, but in a slightly different posture. He's leaning on a railing. But still, the position of the occluded legs is predicted quite reasonably. Now, notice here how for the ground truth, I'm showing you bounding boxes and not ground truth A-modal mask, which comes from the fact that I shared before, which is in the real world, it is hard to label precise ground truth for A-modal segmentation. And so to evaluate the performance of our model on the real world, we derive bounding boxes from our predicted A-modal masks, and then we use the standard detection metrics for comparison, which is average precision. And you'll see the difference in performance is quite significant here between the baselines and our model. And this is because the other methods are not able to generalize well to new objects or scenarios. So my hypothesis is that the real win here comes from the pre-training of stable video diffusion, which has seen lots of real-world data. And then one other thing that I believe helps this generalization is our conditioning on pseudo depth, which, if you recall, is an input to our diffusion model. So concretely, pseudo depth proves useful in 2 different ways. One is that instead of having RGB videos of the scene as input to our model, depth lowers the sim to real gap as you're not relying on unrealistic appearances from simulation anymore. And empirically, this shows up in the drop in performance that our model suffers from on the tau A model dataset when it is either conditioned only on RGB frames or it is conditioned on RGB frames in addition to depth. And two, pseudo depth is actually a very actionable quantity in the sense that it tells you exactly which pixel is in front of which other pixel. And this helps our model extend masks into regions where the depth is lower around the visible object. So for example, here on the very right of the image, there's a chair that is heavily occluded. So without the depth conditioning, the model cannot understand that to the left of the chair, there is a possible occluder. But then with the depth conditioning, it has that information and so is able to extend the mask to the left. And then similarly for this occluded person, with the depth conditioning, the model knows that the mask could very well be extended to the bottom of the image because this is a person sitting inside a car. Okay, so with that, we know how to amodally segment objects and videos. I'll now talk about amodal completion. So it turns out that it is actually not that difficult to also fill in the amodal masks. So you can once again do the same thing, which is fine-tune another video diffusion model with the predicted amodal mask of the object from the previous stage as input, then the visible pixels of this object as another input, and then fine-tune this model to predict the amodal pixels. So this is again easy to train, only this time getting hands on the training data is not that straightforward. So we find a way to create our own training samples. Specifically, we take all fully visible objects from SailVOS, which act as our target amodal RGB pixels. And then we randomly paste other fully visible objects on top of it to create synthetic occlusions. And this gives us the input and output training pairs. So this part of the pipeline also generalizes reasonably well to real-world videos. I'm showing you some examples here from the tau A model dataset, specifically on the top row. And then there are some other very in-the-wild examples. For example, on the bottom left, I'm creating a new object with two markers and a duster, which the model is able to complete quite well. And here is a random video of a penguin, which is quite heavily occluded throughout the video. And then there's Einstein from the Oppenheimer movie and Trump from his presidential debate. So you can guess by now that there's no good way to evaluate the quality of amodal completion in the real world. So we do a small user study where we find that on 20 randomly selected videos from SailVOS and tau, the participants show a 85.6% preference for our method over the only other amodal completion method that exists, which is Pix to Gestalt. But importantly, Pix to Gestalt is an image-based method. Okay, so given the generalization ability of our model and the high quality of amodal masks, you can now use it to almost create pseudo ground truth for real-world data. So we find that in a follow-up work on our method, if you use, so this work shows that if you use our method to compute occlusion rates for different objects in a benchmark that they propose, along with computing the occlusion rate with multimodal LLMs like QuenVL, or by computing occlusion rates using bounding box methods like intersection over union, it turns out that the occlusion rates predicted by our method and this VLM called QuenVL, they're very similar, which kind of suggests that our amodal masks are quite realistic. Finally, with our method, you can now virtualize any occluded object in any video. with some help from off-the-shelf reconstruction methods. So for example, I'm using stable 0, 1, 2, 3 here. Okay, so till now we saw how we can recover a 2.1D layered understanding of the scene by solving a simpler perception task of amodal segmentation and in-painting. But this is still a very object-centric understanding of the world, right? So now I'll discuss how we can model and synthesize the underlying structure of entire scenes through the task of novel view synthesis. So I assume all of us are familiar with the novel view synthesis task, which can be defined as follows. Given a scene from some number of source camera views, we want to synthesize the same scene, but from a novel camera view. For purposes of today's talk, I'm considering a slightly harder setting where there is only a single source view and the target camera is sufficiently far away from the source camera. So you could think of this as an extreme novel view synthesis task from monocular videos. So prior works that tackle this specific case can broadly be categorized into two main approaches. On the one hand, there are optimization-based methods that produce excellent results when the source and the target views are close to each other and the scene is predominantly static. But then they struggle to model simple dynamics, for example, a rotating apple in this case, even from the near novel views. On the other hand, there are feed-forward methods which can hallucinate new regions and do extreme novel view synthesis. But then their 3D consistency is quite limiting because unlike optimization-based methods that optimize an explicit representation, their notion of geometry is quite implicit. And so in contrast to both of these, we propose to decompose the problem of extreme novel view synthesis from monocular videos into two different stages. The first is reconstruction of only the visible parts of the scene, and then hallucination or in-painting of the unseen regions. So for reconstruction of visible parts, we already have tools from SLAM like Megasam that work quite well, even in the dynamic settings. And so we leverage them for doing much of the heavy lifting here. So now all we have to do is learn to in-paint in a 3D consistent manner. So then the question becomes, how does one get the right training data for in-painting? So this would be easy in a world where we had access to synchronized multi-view capture setups. But recall what we discussed before about the scale of such data. 4D datasets which have multi-view information are either very small, like die check, or they exist only in simulation, like datasets rendered from the Kubrick engine. And so instead, I argue that to build a scalable data generation pipeline, using a large corpus of 2D videos is inevitable. So along the same lines, we devise a self-supervised approach to generating the training data, which I'm going to explain next. So for any video on the internet, we can let methods like Megasam reconstruct the scene for us. And this essentially gives us a time-varying 3D representation of the visible part of the scene, along with the camera motion that you can see in red here. And now you can project this 3D representation into any other arbitrary set of cameras, like this one in blue or this one in orange. So if we had, say, 100 points in the original video in red, maybe you're able to see only 70 of them from the camera in blue. So for context, these 70 points, which are visible in both the red and the blue cameras, they're called co-visible points. So then if you were to project these co-visible points back into the original view, you'd essentially get a masked version of the original video. And this masked version of the original video and the original video itself, they again form an input and output training pair. Unsurprisingly, this self-supervised approach is very scalable because for a single scene, you can choose any number of arbitrary cameras and create any number of in-painting masks. And this is not all. So if you notice, even during inference, you can create the same kind of in-painting pairs and fine-tune your model at test time for the incoming video. And actually, this test time fine-tuning proves to be one of the most crucial components of our pipeline, and it gives us a big boost in performance. So now, instead of reconstructing and in-painting to generate the novel view, we propose a three-stage pipeline that first reconstructs, pre-trains a model for in-painting, and then fine-tunes this model for any incoming video at test time. And the fine-tuning is essentially overfitting the model to the test video's appearance and scene structure. So actually, let's spend a few seconds on this particular example. So without any test time fine-tuning, which is the third visual from the left, you'll see that the model in-paints what looks like snow-covered rocks on the right, and then what looks like a human head at the bottom. But then after test time fine-tuning, the in-painted region is much more consistent with the other content of the scene, which is it adds more foliage to the right and more rocks at the bottom. And I'm guessing you're thinking now, why don't we only do test time fine-tuning and no pre-training at all? Because you don't really need any annotations for this task. I want to show you another example here. So this is a video of a corgi from a static camera. So if you were to just test time fine-tune by creating masks, you'll find that in this case, there is no configuration of masked pixels that can teach you how a corgi looks like from the side. So for cases like these, it is important that the fine-tuning starts from a point which already has these priors developed. And therefore, pre-training also is important. So one more thing I want to point out here is that the in-painter that we are building has to do more than just in-painting. This is mostly because the first stage of our pipeline, where we are using off-the-shelf SLAM methods, that stage is not perfect. So for instance here, Megasam produces smeared depth around this robot arm, which results in these highlighted artifacts. And so our model has to work to correct the artifacts that are highlighted. And apart from this, we also majorly use point clouds as a 3D representation, which means that the rendering stage cannot handle view-dependent effects. So when we render a scene, we often see things like the background being visible through the foreground. So for example, you can see humans at the back through Superman's face. And this also has to be corrected in the final model, in the final output. Okay, so I think we have all the bits and pieces now, and let's see how this recipe looks like in action. So first, I want to start with some in the wild or out of distribution results. And here our model is being used in a zero-shot manner. So the first one is showing a generated video from Sora. And even for something like snow in the background, our model can generate its novel views quite accurately. And then the second one here is a real world video of a Boston Dynamics humanoid walking. And the third is a static scene where nothing is moving, but it shows that our method can handle the simpler cases. Okay, once again, the first one up top is a synthetic video from Sora. And you'll notice how the method almost copies over these two humans on the very left into the in-painted region. And then the second one is actually not a great example, but I'm showing you the example here to point out the ripples in the water that are introduced in the in-painted region, which is, again, very physically plausible. And I believe it comes from the pre-training of CogVideoX, which I'll talk about in the next slide. And then finally, there's another static scene at the bottom. This time, this is an outdoor scene, and our model can hallucinate realistically. So for building this model, what we used under the hood is a transformer-based diffusion architecture called CogVideoX. which is much beefier than the stable video diffusion model that we were using before. And we fine-tuned Cog Video X on a collection of 10,000 videos from 4 different data sources, which is Tau, Segment Anything Videos, YouTube VOS, and Davis. And all of these data sets are actually meant for multi-object tracking and segmentation. So that kind of ensures that there's enough dynamics in the scene, and there's also enough dynamics for the camera. And it takes us about 3 days to finish training Cog Video X for this in-painting task. So talking about evaluation, we predominantly used synthetic data sets like parallel domain 4D and Kubrick 4D for evaluation alongside a real-world data set called DieCheck. And I'm only going to cover parallel domain 4D here. So we can spend a few minutes on the setup of parallel domain. So the input is from an egocentric view from a car. And the evaluation view is a camera trajectory that goes from this egocentric view to the bird's eye view. So for both of the synthetic data sets, parallel domain and Kubrick, we are given the point cloud of the scene. So that is what you see at the top right here. And then the job of our model is to in-paint this rendered point cloud in a 3D consistent manner. Okay, I always find the in-painting of the sidewalks and the pedestrians here by our model at the bottom left to be very interesting because these cannot be seen very clearly from the egocentric view. So for an empirical analysis, I'm going to report PSNR here, which is a standard metric that prior work in this space reports. So like I showed, given the ground truth point cloud of the scene, our method produces 3D consistent novel views for these dynamic scenes. And then one of the baselines that we consider is called generative camera dolly, or GCD, which is a feed-forward diffusion-based method that implicitly conditions on the relative camera poses. So you can think of this as 0, 1, 2, 3, but for videos. But like I said before, the 3D structure is not maintained very well in the outputs. So you can see here, I'm screenshotting 2 frames between GCD and the ground truth, and you'll see that there's a considerable amount of difference in the sky region. And more importantly, GCD is not being evaluated in a zero-shot manner because it was trained on parallel domain 4D. We also compare to Trajectory Crafter, which is a recent method, and has a very similar flavor to us, which is reconstruct first and then in-paint. But crucially, Trajectory Crafter needs 3D data to train on, unlike us, where we train only with 2D videos, and it does not have a test time fine-tuning stage. Now, one thing to note here is that when using our method for novel view synthesis, you have to incur a runtime overhead of about 2 hours for the test time fine-tuning stage. And this undoubtedly makes our model slower than other feed-forward methods like Trajectory Crafter or GCD. But in general, our runtime is kind of in the same ballpark as other optimization-based methods. But then, more importantly, these optimization-based methods cannot handle extreme novel view synthesis. So we dig a little bit deeper into this and we study how the amount of fine-tuning affects the performance. So here I'm plotting the number of steps on the x-axis against the performance in terms of PSNR on the y-axis. And we find that in a fixed resource setting, our test time fine-tuning can achieve 96% of its performance, which is the third data point here, in just half of the fine-tuning time. So technically, you could trade off speed with accuracy. And of course, if you have unlimited compute, then this is not a problem because you can always parallelize our test time fine-tuning stage. Okay, so that is what I wanted to talk about today. A few things that I want you all to walk away with as takeaways from both of these works is that, one, to harness the full power of foundation models, we should try to bring downstream tasks as close as possible to the pretext tasks. So for the first work, this meant that we tackled A-modal completion in 2 different stages. First, we only did segmentation, which allowed us to almost reformulate the completion task as an in-painting task. And then for novel view synthesis, also, we reformulated it as a structured in-painting task, which was much easier for the diffusion model rather than trying to understand the implicit notion of cameras and how they affect the view of the scene. And then, two, if you are able to do this, then my work suggests that we should need only a little bit of curated training data for fine tuning the model for these new downstream tasks. And then the fine tuning itself is lightweight, taking about 1 to 3 days. So this wraps up my presentation on my most recent thesis work. And I want to now spend a few minutes talking about the future directions that I'm the most excited about. Broadly, I want to touch on two main aspects. One is how I think we can make better foundation models, and two, which avenues I think should be explored for using these foundational priors. So before even starting with this first direction, I want to define what I mean by better. So better for me means being like building scalable models that can be trained with as much data as possible, including all the 2D sources, which are more readily accessible than any other kind. So I think present day models already handle this, so it's kind of taken care of. But then more importantly, I'm more excited about these models being efficient. And now you can define efficiency based on your real world use case. This could be models being faster to train, faster to run inference from, or occupying less memory, and so on. So my hunch is that a universal solution for efficiency is going to come from introducing soft inductive biases in foundation models during training. And let me unpack this a little bit. So let's take, for example, Genie 3 here that Google released recently. And this is a good example of introducing inductive biases. So in this case, there are 4 rotation controls and 4 translation controls for the video that is generated frame by frame. And here is another video model called WAN 2.2, first and last frame model, which takes in 2 images as input and interprets these images as belonging to as the first frame of a video and the ending frame of a video. And then it's trying to interpolate between these 2 images. So if you almost overthink this a little bit, the task for this model is essentially finding correspondences between these 2 frames, right? So these are the kind of examples of inductive biases that I'm talking about. And the claim I want to make is that with better biases, the models will inevitably learn better representations, which is going to result in more efficient models. So there is some evidence from recent work that if you align the intermediate features in diffusion transformers with pre-trained vision encoders like Dino, you can train your diffusion models 17 times faster. And similarly for inference, I believe that if an interpolation model like WAN understands this level of geometry of a scene, including like view-dependent effects on the glass, for example, their representations have to be 3D aware. And so, for instance, you could learn a lightweight decoder on top of these representations that are conditioned on, let's say, camera poses. So now you have a lightweight renderer that looks at these representations, conditions on the camera, and then generates a new frame for you. And you can basically do novel view synthesis on the fly. So that's one direction that I'm excited about. The other direction I want to talk about is which avenues we should explore given these massively pre-trained foundation models. And I'm going to focus only on their generative formulation. So very broadly, my bet is that we should be doing more with the multimodal nature of these models. So one specific example is a real-to-sim task of building closed-loop simulators from real-world data. So for example, if I saw a video of a robot gripper lifting an open bag of Skittles from the top, then I should be able to hallucinate that all the Skittles will fall off if the gripper held the bag from the bottom. And I think there's a really easy formulation of this from the egocentric view, which I'm showing at the top, which is just reactive replay or reactive novel view synthesis. The other direction that I'm very interested in is long horizon planning. For example, ordering those snacks for you was a planning task for me over a horizon of several days. And that was not all. There was more low-level planning involved. For example, how I should reach the front gate of this restaurant. So for long horizon tasks, I want to think about the interplay of such global and local sub-problems. And my bet is that maybe we'll find that vision in isolation is not a solution to this. So a possible solution could be to plan more abstractly in language, update a local spatial memory, and then predict some low-level action controls to execute these plans. So that's all I wanted to cover about the future directions that I'm excited about. I want to end by expressing my gratitude to my committee for being here today and taking the time for giving me feedback on my work since my proposal. And I want to especially thank my advisor, Deva, for patiently teaching me so much in the last 6 years. And it has completely changed me as a person from when I started. I also learned a lot from everyone in RI, including a lot of friends, but especially my lab mates. And the definition of Deva's lab actually evolved over the years. First, I was surrounded by my seniors, Achal, Piyun, Martin, Ayush, Gengshan, and then I started becoming the senior myself. And I had a lot of fun over the years. Everyone was very nice and helpful, and it was truly a home away from home. I also didn't know that I could successfully mentor other students from master's to high school. And so I want to thank all of my mentees for making me realize that and helping me be a better mentor. Last but certainly not the least, I want to thank my husband, Akash, for actually witnessing every hour of every day of this journey with me. And we are both about to make the finish line, which is very, very exciting. And I'm so lucky to have had tremendous support from you in all the highs and the lows. And also my brother, Meher, who is now here at RI2. He makes me a better sister and always keeps me on my toes to learn new things. And then my parents for giving me a rock solid foundation. I try to be kind and fearless like both of my parents. And then finally, my second set of parents and brother who quite evidently love me way more than they love Akash. So I'll leave you with this slide now and I can take any questions.
Hey, thank you for the talk. So as is customary, we'll start with the committee and furthest away. So Leo, if you do the honors, that'd be great. So maybe we'll start with like a few minutes of questions per committee member. We could do second rounds if the folks would like. Leo, can you hear me?
Leo, are we audible?
Sorry, is this the public part or the private part of the?
This is the public questions.
Okay.
Should we as the committee ask the questions now in public, or do you wait to is there a private session? Just question on the procedure.
Yeah, so the procedure is that there's the public session is now it's customary for the committee to sort of ask public questions. We don't actually have a yeah, we don't have a formal private question session. So any questions you can ask.
Can we have a 2-minute break before we go into the question part?
You know, I actually could go next, Leo. If you want to get a cup of coffee or run to the restroom, I can ask my questions now, and then when you come back, you could go. Does that work? Oops, but I think the CMU room is muted completely now.
That should be fine.
Okay, can you?
Now we hear you. Yeah.
Cool.
Yeah.
Okay, thanks, Carl. That'd be great if you could start us off.
Yeah, of course. Yeah, so really impressive work, actually. Yeah, really amazing results. I mean, I was kind of blown away by some of the results that you were showing. We had a student at Columbia working on some more problems, graduated a few years ago, and And so I know how hard this problem is. So really impressive results. I had some low level and I guess high level questions. On the very first work, I guess that's conditioned on an input mask. You have to say what object you want to track, right? Does it would the same type of technique work where you have to where it's kind of self-starting? Like what would it take for that to work?
As in if you did not have a starting modal mask
Yeah.
for the pipeline? Yeah, I think that's a harder task for sure, because now you also have to track the object and you're basically doing all the heavy lifting that Sam too was doing for you to get the modal masks. I would say that a user input in the form of a prompt, let's say maybe a click on an object of interest, would still be helpful. And that also that kind of reduces the problem to like the single object tracking problem that we used to look at before. Can we disconnect the owl? Just a second.
Yeah.
Okay. Yeah, so I imagine that using a generative framework for getting amodal masks would be, I think that is a non-trivial problem to solve, actually.
Well, it kind of leads into my next question, which is, I guess, is about like representation and about the 3D world. And so I think like your work kind of takes this very implicit view, which is as long as I can render the view, there must be a 3D representation. You don't really care kind of about the structure so much about that representation. Just as long as you can render it from a different view, right, or remove a occluder, then that's your representation, right? But I was wondering about like limitations of that. Like one thing I was thinking about is like, could your system handle kind of a container relationship, right? You put something in a container and then the container moves, and you still want to understand that when you pull it out. So do you think this kind of like implicit representation? I know this word implicit is a little bit overloaded, but it's sort of this implicit representation. Is that kind of good enough to basically solve all these types of like spatial problems?
Yeah, I think the answer is no. Like even the current work is has a lot of limitations, and you pointed out correctly that actually there is occlusion resulting from containment that we cannot handle. Also, mostly because we do not have RGB image as an input to our model. So that is also one limiting factor. So like you would have seen examples where there are like 3 upside down cups and there's an object in below all of these cups, and then you try to shuffle the order, and then so our method cannot maintain like the correct sort of amodal region for the object. Yeah, and so to be honest, with the current representation, I think you can go quite far in modeling like almost linear occlusions, as long as the objects follow a linear dynamics model while being occluded. There is some it is also quite data dependent. So for example, even though people are non-rigid, there are a lot of examples in our synthetic data set from SailVOS of humans, and so that non-rigidity, even though it is nonlinear, is kind of learned very well by the model. But then yes, it's not like a universal solution, and the setup is still limiting.
I mean, I think one thing that makes this problem so hard in some ways is that you, like, by definition, lack supervision, right? Like when there's partial occlusions, you kind of get free supervision because you can see where things are and you can layer stuff on top. But when you start getting the more physical things, you don't have a camera inside the box or in these occlude cases, so it's hard to learn that.
So I would, I mean, like a supervised setting is like the ultimate gold standard that we all want to have. But I feel like even if there was enough data coverage in the SailVOS data set, even for examples like containment, like we talked about, I think it would work Yeah, my bet is that having that kind of data would allow you to handle some of those cases, but then yes, like I don't think you can do better than having a supervised setup with this current kind of representation.
Yeah. Oh, sorry. I guess when I said no supervision, I mean there's not even self-supervision in some ways, right? Like you just don't even know inside. If you have an object inside of a box, you have no idea where inside the box it
Yeah,
is.
yeah. I was trying to run a lot of examples for the visuals here, and they kept failing because there were all of these kind of examples. Like someone was putting all different objects in a box, and yeah, there are limitations.
So, and then I guess last question I had, which was, I don't, maybe I missed it. I was eating lunch during this as well. But what were some of the main kind of limitations that you saw?
For the segmentation work or for
Yeah,
the
yeah, or I guess both.
Hmm. So for view synthesis, I think our current pipeline depends a lot on how good the reconstruction is. So there are instances where we see that because of how smeared the depth is, even our outputs start looking that way. And there's not a lot of correction that our model can do. So at some point, it is kind of dependent on the first stage of the pipeline. Uh, yeah, and then for A-modal segmentation, I think, yeah, one of the biggest limitations is like occlusion resulting from containment. The other thing is also that except for people, like I showed an example here where the legs of the human were not visible throughout the video, except for that class of object, I think for all the other objects, you need to have at least one frame where the object is fully visible.
Mm, mm.
And so for people, only because of the amount of data that you kind of bypass that issue. But then for all the other examples, it works the best if you have the object visible at the starting of the video and at the end of the video, and then there's some occlusion in between.
Great. I guess maybe I'll stop asking questions here, but I'll keep thinking of some more.
Okay, now perhaps Carl asked this question when I was away, but in the first part, the model mask and completion, are you able to do something when the object is fully occluded? That is, it seemed that you didn't, I mean, you showed an example at the very beginning in this Mumbai scene where it seemed that the motorcyclist at some point was fully occluded and yet you were able to reconstruct the mask.
Yeah.
Didn't
Yeah.
understand from
So
your description how you handle, essentially you have to do some motion prediction in the, I mean, for the invisible interval.
yeah, yeah. So you're right. Like that was one result from our method where that motorcyclist was very heavily occluded. And then I showed another example on this slide of a laptop being fully occluded in a few frames. So this is actually a very good example of like a deforming or a non-rigid object that undergoes full occlusion, and yeah, our model is able to predict the masks during that. And actually, it is like it is easy for our model to predict the masks during full occlusion if there is enough like evidence in some other part of the video that like what that suggests what the actual shape of the object was while it was fully visible.
So you're predicting the masks for all the frames simultaneously.
Yes.
Yeah, okay. Yeah, so you do have context about how the object was, yeah, before and after a particular frame. I see.
Yeah, so the underlying model here is stable video diffusion, which takes in 25 frames of a video as input, and it predicts 25 frames of a video as output. So yeah, there are attention layers that talk to each of the frames.
Okay, good, thanks. And then in the second part, in the next view prediction, I didn't quite follow what is the input to the fine-tuning stage? Is it just the output of the completion or some more information like the masks? And I mean, you mentioned that you correct errors even if even outside the masked areas. And I didn't quite follow how that happens.
Yeah, okay. So I think the in painting stage that I'm saying here is actually only during training. So during inference, we don't have to run our model twice, but we take this pre-trained in painting model and then we fine tune it for the given video at test time. And then I was trying to explain here how you can like artificially create input and output training pairs for this given video. So it's basically just you are just masking out your input video, but now the mask is just like has a more 3D structure to it
Right.
rather than being a random like mask.
Mhm. I see. Um, and I'll ask one last question about your future plan slides. Uh, um, I mean, it's a big question how to use foundation models for these downstream 3D and 4D tasks. And um, at least in my experience, foundation models today are imperfect. So the question comes up, how do you learn what to trust and what not to trust in what they tell you? Essentially, I feel it's like you bring a new worker to a team and you have to understand what this worker can do well and use that and what this worker cannot do well and compensate for that. Do you have any thoughts about this?
That's a good question that I have not thought about before. But I guess you're almost asking about how can we maybe one quantify the uncertainty from the predictions from these models, and then how can we inform like downstream tasks given this uncertainty estimate? So I think an inefficient way of getting uncertainty is to like just do your forward pass multiple number of times and get different predictions and then compare these different outputs to like see how or which regions in the video are more uncertain than others, like how much agreement do you have between these different multimodal samples in the output. But how to use them for like tasks that maybe I'm talking about here, I don't have a great answer for that. So it could be the case that for real to sim transfer, I guess like a cop-out answer is that maybe you sample so many times that eventually one of these times you are able to generate the right answer. So for example, for this maybe closed loop real to sim transfer, um, yeah, one of the solutions could be like give like predict 10 samples from the video, and then you expect one of these samples to at least give you like the correct answer. But both of these are very inefficient ways of handling uncertainty.
Yeah, I'm not sure if uncertainty is always the answer because my sense is that this model sometimes can be very confident and very wrong at the same time. That is, but of course, there are works that try to estimate the uncertainty in the answers. Maybe one possible approach may be to ask the model for more than you need, but then ask things that are correlated so you can check the consistency of the answers with each other through maybe some lightweight verifier or some other tool.
Yeah.
This
Yeah, that makes sense. I think another like solution is also to, like I said, add more controls uh, to the training task itself, right? So that it knows that these physical quantities have to be related to so and so output, and so there it yeah it inevitably has to learn to link the controls to the output, and so maybe that helps learn better foundation models.
Okay, Tarasha, thanks on my side.
Okay.
So I really like the approach. I do have two questions. So the first one is just with a mask, and then we fine tune the diffusion model, to complete, right? And then also textualize.
Yes.
Yeah, I think this is really nice. But the focus of the one big track, of course, and then we just complete. And that's why I like how you said, especially in the easy to do that.
Yes.
Because it's a problem that you've been working on some time and the result is so cool. That was really amazing. So I guess some of the students I would ask is the following. Can we use your example? And let's say someone said we have one back in the object, and we don't have to be able to texturize that object. So if we run foundation codes on your output object triplet, will be much better pose estimation for the object than if you run the original video.
Yeah. I actually had a really good slide for this, but I think I removed it. But the short answer is yes, you can very well do that. So I tried running the same method on a bunch of like first person view videos where I myself was interacting with objects. And so the hand reconstruction, I have to admit, is not that great. But for the objects, as long as they are quite big in the entire video and they are not small objects, that works fine. Yeah, they're not too. Yeah. And actually, it shouldn't be too hard to also handle very small objects. Exactly. So like right now in SailVOS, we had to remove really small objects because there were so many of them and the occlusions were so high that maybe you would see only literally 1 pixel in the entire video. So we had to remove those kind of cases during training. So then the model gets like quite biased towards, okay, like imagine there's a case where there's a very highly occluded object, which is really big, but then you can only see a single pixel of it throughout the majority of the video. So in those cases, it biases the model to think that the object must be small itself. And it like this pixel could not have belonged to like this really large object. So yeah, I guess like for improving,
I know the SailVOS is the answer for occlusion mask. So I put my keys, they're gonna tell what is the occlusion mask of my keys while I'm delivering.
yes.
I see. So we do have this mask training that you'll find.
Yes.
I see. I don't know. I think this is interesting because this is like very interesting data. This interactions.
I think there are
slow, right? That's the problem.
Yeah.
Function process fast. Now here is. So this is the only downside for this video. Just really slow.
Yes, I also want to make them efficient.
I see. Okay, so this is the first question. We can discuss also more offline, but some question about the second part. Because that we get it, like we get the video and reconstruct it, and then we render it, and then we find for visible pieces, we render them back. So now we have a masked video, like a video with masks, and then a complete video. But we can also just try it random masks as well.
Yes.
And they can be self-supervised, right? And then we try essentially. What do we try? Do we try the video in paper or we try a view? Like I have a view given, and then I paint the outer view.
Yeah. So here we are only training an in painter. So this is
not attended to the other. So in that sense, it's different that camera only that attends on one device than the other.
Yes. Yeah. That is right.
And then once we put that in painting happens independently on the different sample camera trajectory. So there may be some misalignment there.
Can you say that again? The masking happens.
The intent, so I have a nominal molecular video and then I put random cameras and then I render incomplete views and then I inpaint them independently and maybe the
they are
super consistent or something.
Yes, that can be the case.
This be extended to something that actually but then it's possible to find supervision for the thing that we have one view complete and then we have a synchronous parallel view, but this is impossible to supervise, let's say.
Yeah, this is impossible to self-supervise with like the current setup. Where we are using only 2D videos.
But then my question is, why would we need to use this method to train a video in Blender, given that I can take a video, mask whatever I want, and then fill it in?
Yeah, so you could actually do that. So one, at the time of our submission, there actually did not exist a video in Painter. Although they exist for like image diffusion models, like stable image diffusion. And then also, it turns out that the structured masking is actually very helpful for in painting specifically, because if you were to use like other masking strategies like random masking or tube masking, which video MAE uses, that is quite suboptimal.
Very nice. So this mimics a little bit the geometry in masks that are generated. So
Yes.
it gives you more distribution to how you're going to use it later.
Yes, exactly.
Okay, yeah, now I got it. Yeah, I mean, I really like that as well. And then the future works, I didn't really understand the counterfactual part.
Okay.
The one with the, I mean, that would be amazing. Yeah.
Oh, like the
So
reactive
what you
replay.
have there, yeah.
I see. Okay, this one. Just a second. Was it this one?
Yeah,
Okay.
yeah. So what would you trying to say here?
Okay, so I think the visual does not do justice to what I'm trying to say. So technically, imagine that you're seeing both of these videos from an egocentric view, from a camera on the robot gripper. That view would look something like what I'm showing at the top, but they are not videos here. So if you had this kind of data for the same for like the same scene, but the world is unfolding in different ways for the same scene. My hunch is that you can like solve this task as a novel view synthesis task, but now you would be doing the synthesis only for like the static regions, but then you're allowed to hallucinate all the dynamic like foreground objects. Is that making sense? So if let's say I was given this video on the left from the egocentric view, if I were to do novel view synthesis on it again from a different like 3D location of the camera on the robot gripper, then I should be able to like predict what would happen next, even if that does not follow what already happened in this one rollout of the world.
All right, so you're saying the synthesis should not just be, oh, I move the camera, but rather, I play different scenarios.
Yeah. So for example, like in the first video that I showed of the Mumbai scene, so in this case, if I drive way too much to the left, I should hit into something.
Yeah.
And that should be my novel view. That is my claim.
I see. To really use counterfactual.
Yes.
Yeah, so these are my questions. I think it's really nice and novel to bring video models into 3D geometry. Thank you.
Thank you.
Yeah, first of all, I think great talk, very nice results. I think I've tackled these problems a while back, and I would have been very, very happy to see the website in those projects. So, yeah, it's really important to see. Maybe one specific question about the second project first.
Okay.
The high level approach is you reconstruct and then you project, right? And then you implement. The Superman example that you had was showing to some extent that you could handle artifacts where your reconstruction wasn't perfect.
Yes.
There's some thing that is in front of you need to remove something. But correct me if I'm wrong, but my guess is this will not work for even larger viewpoint changes where there's like an entirely wrong structure that gets projected. And so a concrete example is you see front of a car. And those are points you reconstructed, and you say, what happens if I walk back or any objects in the reconstructions that come very back?
Yeah, you're right. So so for front facing views where you can only see like from the front what is happening for an object, our method kind of works only till like 90-degree novel view synthesis.
Okay.
But then because it is a point cloud representation most of the time, if you pan the camera too much to the back of the object, you will see the same object like laterally inverted, right? And so yes, it would not work. But this is the case for inward facing like 360-degree scenes. But then I had an example here. Wait, is this playing? Okay, this is not a perfect example, But then for outward facing like 360-degree scenes, you can still do like
Sure, but I mean, maybe that's the thing where the reconstruction. So maybe let me give a slightly different example. People on Zoom might not be able to see, unfortunately, but there's this laptop on this table and there's floor below. And then maybe from a specific viewpoint, I'm seeing a bit of the floor, and I'm seeing like there are parts of this table that are being offloaded. And from a different viewpoint, I should be seeing the table, but there's a part of the floor that I saw from a different viewpoint, which sort of also projects onto these pixels. And so, you know, there is supposed to be this table that is supposed to be in paint, but those pixels already have the floor projected. So it's not even a 90-degree change. It's, you know, it's more to do with
which point is in front
Yeah,
of
as
which
in-
point along the ray. Is that?
there are the points that you project. If there's something in front of those points that should be kind of constructed or generated, and in painting models sort of fundamentally will have a very hard time doing that.
Yeah, I see your point. It is, so I guess once again, my answer would be like if your input data has those kind of examples and during training you are trying to actively fix that kind of an artifact, then yes, it would handle those cases. But yeah, I mean, in general, the formulation like still has
Okay, so on
bit of
that note, like would it, I mean, I would assume that the self-supervised way will never have this data, correct?
yes,
Um,
that is true.
So I presume you will need to. So okay, maybe two-part question there. One, presumably an approach where there is self-supervision plus a bit of supervision could in theory overcome this.
Yeah, definitely.
But what I want to know is if it is possible, because like later you were saying, right, that your inductive biases are better, etc. And here I would say it's an example of an inductive bias that could be wrong in some systematic settings. So is it easy for the network to overcome it where you're saying, hey, I project this and the floor is visible at these pixels, the network has to learn to say, no, no, no. There has to be a lot of table pixels that actually should come over this. So is it actually, given this projection inductive bias, is it a good inductive bias in general? Would it be very hard to unlearn it in settings where you have to unlearn it, I guess? Very amusing question.
So to be honest, like, yeah, data is kind of still like the 50% fixed to this. Even in our setup, like almost all of the videos that we are training for, we get the reconstructions from Megasam, and Megasam is not perfect at the boundaries. So even though we have that kind of data, our model is like still not quite able to handle like the smeared artifacts. So I think data is like the first step that I would go towards. Yeah.
And then I think the second generic question, because I think your thesis is cited more on the 4D understanding, is like coming from the 2D understanding and 3D understanding, there are some canonical tasks that people agree upon, right? That as a community, let's tackle these tasks, segmentation, detection, etc. In 2D, in 3D, I would say we've kind of converged on novel view synthesis and maybe sort of 3D reconstruction, including the depth as well. So based on your thesis in general, or based on your reading, what would you say are the canonical 4D tasks that I think the community should be tackling? And I would add a sub-question to that, which is, are they any different from the canonical 3D tasks just done at every time step? Because like novel view synthesis, reconstruction, to me, those are just saying, hey, let me take the typical 3D task and say, okay, I should be able to do that at each time step.
So to be honest, I think maybe this is controversial, but I think even for 3D, there could be like more tasks other than just novel view synthesis, which I feel like is kind of solved in a very simple setting where the novel view synthesis is just interpolation between input views. So
I mean, there are flavors of this, right? Which are generative version of novel view synthesis, like in 0 and 3D.
oh yeah.
So I would also frame that under novel view synthesis.
I see. Okay, yeah. So in that case, like for 4D, I would say like novel space-time synthesis is what I think is the right task, which is not what we are solving here. So by novel space-time synthesis, I mean that you should also be able to interpolate in time and maybe also extrapolate in time. And so you are given, let's say, time steps 0, 5, 10 as input from 3 different camera views. And you want to synthesize time steps 1, 2, 3, 4, etc., etc. So that would be a good task, along with some extrapolation that I kind of believe in.
Okay. Cool. We want to ask a quick question, trying to relate the two projects we focused on. So one thing you didn't quite emphasize, but I think it was looking underneath the surface, which is like the role of data being real versus synthetic. Because in your first project, you made use of Sail VOS, which is a total
Yes.
synthetic data set. And then in the second one, definitely emphasized the fact of like being able to self-supervise from real 2D videos was a game changer. And so looking forward, thinking of that slide you showed of like, we have way more 2D data, we have a tiny amount of 3D and even more tinier 4D.
Yeah.
Yeah, it feels like you use a mixture of both those kinds of data. And like looking forward, where do you think real versus synthetic plays into this?
Okay. So I think like the best solution will not be just training on synthetic data or just training on real world videos, because I think synthetic and simulated data can give you much more like supervision, explicit supervision for different physical quantities and tasks. And real world data, of course, like helps you like fine tune your training distribution to be more like relevant to the real world for the tasks that you're going to do. So I think maybe a universal recipe will look like you do a lot of pre-training on both synthetic and real world videos as much as you can. And then there's a little bit of fine tuning for your downstream task, maybe only on real world videos.
I see. I was almost going to suggest the opposite. Because I thought what you're suggesting was that, giving back the statement that Katerina emphasized as well, is that like fine-tuning these models is frustratingly easy. Which I think is also this unusual take-home message that you can tune these things in 1 or 3 days. If that's the case, it also seems like you're not using a lot of data for fine-tuning. And so it seems like one of the recipes that suggests is, okay, download these models trained at scale on huge amounts of 2D videos. But then you want to fine-tune them on high quality data where, I don't know, you could re-simulate what would happen if you grab the Skittle bag in the open end versus the closed end. And for that, it almost seems like much more, like simulated, I don't know, game engines where you control everything, where you can have do-overs and you can explore counterfactual.
Yeah, so specifically for the task, I don't think you need different rollouts of the same scene, even from simulation. I think there's a way to do this, not clear in my head right now, but I think there should be a way to do this with just real world videos. But then I think what you're pointing out, which is very lightweight amount of fine tuning on very less data, that is mostly to align your pre-trained model to a downstream task, right? Which I'm also suggesting should be done on real world videos. But then I think for pre-training, there's no reason to not use whatever data is available. So I would like go ahead and use all of these, or synthetic or real for that pre-training.
Cool, we will open up to questions from the general audience.
Actually, I have one additional question. So,
Okay.
so is this what you meant is the following? Like when we have multiple views, we condition on one view to generate the other view, like camera dolly. But maybe what you meant with your hallucination part is that you can condition on one realization of the scene to more easily generate another realization of the same scene.
Yeah.
So in context video generation, basically, per se. In context meaning like in context of a related.
Yeah. Yeah, that could be like one way of saying that. Yeah. But mostly the idea is that, yes, I want to learn from how a single rollout of the world was. I want to learn to generate how it could have been. Yeah.
I see.
From other actions.
Generate them from scratch, just
Yes,
like frame 0 and text.
Yes.
More general questions?